Hi guys. I'm gonna be doing the same thing I did from the last chapter. And so right now I'm gonna be talking about vectors. Um, so yeah, let's just get to it. So the first thing is that here it says a vector is a quantity that has magnitude and direction. And to describe the velocity of object, we need speed and we need direction. And other examples of vectors are force, displacement, and acceleration. So basically, it has this thing that we call a magnitude, which is the extent, and then the direction, if it's left, right, up, down, northeast, northwest, wherever. And then the velocity, it has kind of like how this thing's like synonymous, right? A vector is kind of like a velocity. Because a vector has a magnitude, which is like the extent of something. And this is something abstract, but here it's more practical. The velocity, speed, that's the extent, how fast. So this is the extent. And direction is the same for both. So basically, an example of a vector is velocity. And here we have other examples. We have force, which is a vector. Displacement, which could also be a vector, and acceleration, which apparently is also a vector. But yeah, I didn't study physics, so you guys helped me with that. Okay, and then now we're doing geometric description. So you know me, visuals first before the algebra. So a vector is basically an arrow. It's a line with an arrow. So a line with an arrow. Amazing. That's a vector. This thing's a vector. Okay. It has what? The length of the arrow represents its magnitude. So let's say there's a vector. The length of this arrow is basically its magnitude. Yeah, that makes sense. And the arrow points in the direction of the vector. So that arrow over there, this thing is the direction. I don't know where this is pointing to. Like northeast, maybe? I don't know. But that's the direction. So to be more practical, maybe we can say this is velocity. If this was velocity, then the length of this would be like the speed, how fast it's going. And then this would be where it's going. Where it is going. Right? I don't know acceleration. We could do, I'm kidding. Let's only do speed. Okay, and then, yeah, so this is just notation. So if it's a vector, we can make it bold, like that. Or this thing with an arrow, which represents that, oh, when people see this thing, oh, okay, it's a vector. And then now we have an example here. So a particle moves along a line segment from A to B. The displacement vector, so here we said that vectors can be speed. I'm kidding. Vectors can be velocity, could be displacement, could be acceleration. So this thing is displacement. Right? And it has this initial point. Actually, both of them are displacement. It has this A initial point and B, the terminal point. Also, It's also the tail and the tip. Yeah, so the tip is the arrow, the A is the one without the arrow. And then UCD is, yeah, it's a similar displacement vector. It has the same length and direction as V, even though it's in a different position. Wait, it's in a different position. This one's this one's here, and then this one's here. So they're parallel, right? And we also have this thing called the zero vector, which is basically zero. It has a length zero. And if it has the length zero, then it has no specific direction. It's not moving. If we want to be more practical, let's say this is a car, didn't move anywhere. If it's not moving, then where in the world is it going? Right? It's not moving anywhere. It's not going north. It's not going south. So yeah, that's that. We can combine vectors. Suppose particle moves from A to B. Yeah, this is a physics based textbook, so they use this thing called particle. But anyway, this particle moves from A to B with displacement vector AB. So we can draw that. Say this vector. The tail, I'm kidding. No, I'm right. The tail and the tip, the initial point, the terminal point. This is the vector AB. And you have this particle that moves all the way to B. And it changes direction from B to C. Right? So how does that work? Well, actually, we have a graph here. Yeah, let's use that. It changes direction from B to C. So if you look here, that particle goes from A to B. Once it reaches B, it's now going from B to C, right? Oh no. Yeah. And the combined effect of these displacements is the particle has moved from A to C with a displacement vector AC. And now we have this thing where we add AB and BC is AC, right? So this thing AB, BC, AC. And it's logical, right? Because we're talking about displacement in this case. So you went from, oh shoot. You went from here to here. Either way, you could take this route or you could take this route, but what's important is you're not in the same position. So let's say if this was UW, this was, I don't know, Bothell, this was Tacoma. Let's say this is Seattle, UW Seattle. From UW Seattle, you go to Tacoma, then you go to Bothell. Or you could go from UW Seattle to Bothell. The displacement is this, but the distance could be this from UW to Tacoma to Bothell, or it could just be this from Seattle to Bothell. I don't know. I'm not from here, so I don't know how long each one takes, but yeah. And this is what we call vector addition because we added two vectors and we got a vector out of it. And here it says if u and v are vectors positioned, so the initial point of v is terminal point of u. So we're saying here the initial point of v, this is the initial point, the tail is the terminal point of view. So the tail of V is the tip of U. Then the sum is U plus V. So we can do that Seattle-Bothell thing again. So this could be Seattle. This could be Bothell. This could be Tacoma. Right? We could go to Seattle, Tacoma, then to Bothell. We could go Seattle to Bothell. So that's the idea. And another way of doing this is this way. So we start at U. Okay, wait. This is what we call the triangle law. I know, very original. Because it's a triangle. This is what we call a parallelogram law. Which is also very original. So we start here. We go here. Then we go here. This is basically what the parallelogram is. You have a V, you have a U vector, and then you can add them with this thing. But then you just connect it back. So it looks like a kite, right? That's basically all that's doing. Okay, and then now we have the sum of vectors AB. So how do we draw that? Well, yeah, here we can see we have this vector A. We add it to this B. And then now we get this AB. So here we can do the Seattle thing again. Seattle, Tacoma, Bothell. Right? Then same for parallelogram. We have an A that goes there. We have a B that goes there. And then we have this thing. Then we just connect them back. So that's what that is. And now we move on to scalar multiplication. So if C is a scalar, V is a vector. Then scalar multiple CV is the vector whose length is C times the length of V. So the reason why we call this scalar is because we're multiplying it to the vector. And it's just so that the scalar is not the same as vector. Because if C was a vector, V is a vector, then it's confusing. So that's why we call it a scalar. And it also makes sense. Because if you're multiplying something by something, you're scaling, right? Like let's say we have this line from my last video, y equals x. But then we want to, let's say, make the line y equals 2x. So we kind of scaled this thing by multiplying 2 to x. So it becomes a bit steeper compared to y equals x. And you can check that out. Just go to desmos.com. And you can try plotting it for yourself. So yeah. And the direction is the same as v. If c is greater than 0, and opposite if c is less than 0. So let's say we have this c. Let's say c is 4. V is v. And we have this vector. Wow, nice green. This is the vector for v. Right? This is positive. But the moment we make it negative, then it basically just goes the other way around. Right? So it changes direction when we make our C negative, or positive. The direction varies based on the negativity or positivity of C. But if C is 0, then we have this thing again from earlier, the 0 vector. So it's basically nothing. And it makes sense. When you multiply, let's say you have CV, C is 0, you multiply 0 to V, that's 0. Anything you multiply to 0 is 0. And here are some examples. V to V. So you notice here, V, this is half of this one, right? And then this is half of this one. So you see how the scaling happens? It changes the length of the vector. And then when we made it negative, now the direction changes, but it's still the same length. And then yeah, we have a negative 1.5. So here we see that real numbers work like scaling factors. That's why we call them scalars. Exactly what we mentioned, we're factoring something by a real number. Two non-zero vectors are parallel if they are scalar multiples of one another. And we kind of show that here. This is a scalar multiple of one another. Because there I just multiply this by 2. The other one's a 1. Another one's this one. And then another one is this one. So we're just multiplying something. Or we're scaling something by a factor. Okay. So that's addition. Now we move on to subtraction. So by difference, u minus v, we basically mean u minus v is u plus negative v. Okay, so let's say this is my u. We have a u here. We have our v here. Now how do we get u minus v? Well, let's say this is my u. I don't know, we just copy this thing. My v here, and then what did we say about the direction changing? That means this is negative v, right? So if this were u, and then this were negative v, because we just connect it, I'm bad at drawing, then that means this is u minus v. Yeah, same idea here, it's just reversed. But essentially, it's like that. We could also do it this way, where we add v to u minus v, and then we get u. We could do it that way too. Because when you add v plus u minus v, this is just u equals u. Because this thing turns 0. And u equals u makes sense. Because they're the same real number. Right? So we have v plus this u minus v. So here's how we do it. We have v plus u minus v is basically u. So if this again were Seattle, and then what was my Tacoma, and then this were Bothell. Right? It's the same idea. And then we have this parallelogram law too. So we have our u, we have our v, and then we get the opposite, and then we have our u minus v in between, and then we just connect it, right? Okay, if a and b are vectors, draw a minus b, minus 2b. So we're given A and 2B. So actually, the simplest way to do this is just get A and then get the minus 2B. And then you just complete the thing. So again, we got A, we add the negative 2B, and it's basically A minus 2B. So in the end, we're still summing, right? So this was Seattle. This was Tacoma. And then this was Bothell, right? So it's the same thing. Okay, or we could do it this way, actually. Because 2B minus 2B is just 0, so this would be A equals A, which makes sense. You could do it like that. Now, how would that look like? Well, it probably look something like this. We have a 2B, so if this were B, 2B would be like this, right? And then we add an A minus 2B. But again, we don't know what that looks like, right? So what can we do? We can actually modify this. Minus A is equal to negative of this, which is just 0. But yeah, minus A would be like what? Right here, right? And then yeah, so once we get that, we just reverse the whole thing. Yeah, pretty much. But honestly, the easier way would be just this one. Yeah. But you can definitely do it that way. I think, yeah. I think you can. Okay, components of a vector. So we want to treat vectors algebraically. If we place initial point of vector A at origin of coordinate system, then terminal point of A has coordinates A1, A2. So now we go back to our 3D thing. So this is our 2D. This one's explaining 2D, right? And then this one's 3D, because we remember in space, we have an ordered triple. We need 3 coordinates that will characterize us, that will give us a point in space in 3D. These coordinates are components of A. So here's the 2D version right here. And here's the 3D version. So the 2D is just a regular plane, 2D plane. And here it's XY plane. And we have this vector A. This is the tail, this is the tip. And we have this point here that's telling us this is A1 or a subset 1. This is a subset 2. And in vector notation, well, we're just adding this like arrow thingy. Just to say, oh, this is a vector. And it's the same for the 3D version. Right? So here we're going A1, so in the x-axis. And then we're going A2, which is in the y. And then we're going A3. So how does that look like? Well, probably like here is A1 distance. Here is A2 distance. And then up here is A3 distance. And if we connect those points together, we have A1, A2, A3. Right? Okay. And here we say that in 2D, all vectors are equivalent to OP. So this one. So this is O, this is P. Yeah, the vector OP, which has the point 3, 2. And then here it says OP from origin to point P, 3, 2, is a position vector of P. So this is the position vector. What do we mean by position vector? It's basically the original thing. It's the one that's on the origin. The tail is on the origin. At least from what I've learned so far. But you guys can correct me. Yeah. I actually haven't finished these notes. I'm gonna finish it while we're I'm gonna finish it on video. Okay. Then we have vector. Okay, so that's 2D. Yeah, that's 2D. And then here we have 3D. So in 3D, we have this OP. Oops, that's ugly. OP. And we have A1, A2, A3. So this is the position vector. Why? Because it's on the origin, similar to this one. It's on the origin. Now, what's another representation? It's this vector here, right here. And it's similar to here. These are various representations of this original one, or the position vector. So they're like, what, carbon copies? But yeah. So this is another representation of the original. And this other representation, it has an initial point A. So here, the tail and the tip is this B. So it's A with the points x1, y1, z1, and B, which is x2, y2, z2. All right? Why did I do that? Then we must have, okay, so this is the stuff, right? Because the origin has the point 0, 0, 0. Now, what's the distance from this point to P, A1, A2, A3? What's that distance? We could use distance formula, but we don't need to, right? Because we can just add each of these with A1. So just add A1, add A2, add A3, right? We don't have to do distance formula, but we could. And so same idea, since this is a carbon copy, this is a copy. So we have this A that has x1, y1, z1. Let's make it purple. We have A, the point A, x1, y1, z1. And we have B, let's make it green, x2, y2, z2. Now we add the same thing. We add A1, we add A2, we add A3. Because they have the same distance, right? This one has the same length as this vector. This vector has the same length as this vector. Because they're equivalent, that's why. So how would this look like? Well, if we add them, let's write it nicely. X1 plus A1 is equal to x2. Y1 plus A2 is equal to y2. And z1, okay, plus A3 is equal to z3. I'm kidding. Z 2. And then now we have this thing, right? And then we just do a little bit of algebra, and this is the distance for each point. A1 is x2 minus x1, A2 is y2 minus y1. You get the story. It's a story. And we have this summary that if we're given some point A and some point B, then the formula for, well, the vector is this point. It's the point x2 minus x1, is the point with x2 minus x1, y2 minus y1, z2 minus z1, right? So that's what that is. Okay, now I'm going to continue my notes from here because I haven't actually learned this other topic. But it says here, we're going to go to example 3. I'm going to do that. So here in example 3, okay. So disclaimer, this is going to be new. So I might make some errors. Please correct me. I'm just documenting my learning. So it says, find the vector represented. I'm looking at my textbook. By directed line segment. We can say vector, but we'll see. Maybe it means something. By directed line segment with initial point so it has this initial point or the tail 2, -3, 4, and terminal point. Oh, we just have to find the vector. So we just use the formula. Yeah, it's basically a numerical example, which is -2, 1, and 1. Yeah, so we just use our previous formula to find the vector that represents this line segment, right? So this previous formula says, given A and B, representation is their corresponding coordinates subtracted to each other. So that means, well, this vector is 2 minus -2. That's our x. That's our x2 minus x1. -3 minus 1. And then 4 minus 1. And then we have 4, -4, 3. So that's our vector. Right? Or am I wrong? 4, wait, my textbook says it's wrong. I don't know why. A is -2 minus 2. Oh, wait a minute. 2 minus -2 is 2 plus 2. So, don't know why that's wrong. Huh. And here it says -3, or I'm just, my addition is just bad. 2, no, it really, okay, that's weird. Yeah, that's weird. Okay, and then -3 minus 1 is -4. Oh, I see what happened. Yeah, it subtracted it in reverse. So I should have done it the other way around. Or it might be the same. So I do the B first, and then I subtracted the A. Right? Yeah, I think 0 minus 3. Yeah. Yeah, so there's actually something missing with the formula. Just to make it precise, it's the absolute value of each of these numbers. So that whatever I subtract it with is going to flip the sign around. So even if I subtract it with AB, so let's say I do B, right? B minus A. So then that's going to be -2 minus 2, 1 minus -3, 4, kidding, 1 minus 4. Then that's going to be, without the absolute value, -4, 4, 3, -3. Now, if I did it the other way, which was 2 minus -2, 1 minus, no, -3 minus 1. Yeah, because I was wondering why are the signs flipped around? And then 1 minus 4. No, 4 minus 1. This is, yeah, here I'm trying A minus B. So this is 4, -4, +3. And then if I do an absolute value, actually, no. No, I'm actually wrong. Yeah, it really has to be B minus A. Yeah, it's this is the answer. Yeah, because it specifically says, it's explicit. The B, we subtract it with the coordinates of A. So yeah. So I'll read the instructions next time. But yeah, so this formula was correct. Yeah. Okay, that's that. Previous formula. Okay, then what does the textbook say? The magnitude or length of vector V is the length of any of its representations. Yeah, it's the length of any of its representations and is denoted by the symbol. So is length of any representations. So like from the previous one, they have the same lengths, right? And denoted by symbol. So this is something it's, haven't learned yet, but it's this symbol, or it's the one with the two vertical lines that's in between the letter. And by using distance formula to compute the line segment, or the length of a segment, we have these following formulas, right? So using distance formula, we obtain these. So these are the formulas, and that is in 2D, so the length of two-dimensional 2D vector A is just a name. Is a what? A which has A1, A2. So we know this is in 2D. Is. So now we use this symbol from the earlier one. And we have A squared plus A2. And this makes sense, right? Because if this were, let's say, a Cartesian plane, we have this origin here, which is 0, 0. And we go, this is A. This is what is this? This is A1, A2. In 2D distance formula, this is A1 minus 0 squared, A2 minus 0 squared. And so that would just be A1 squared, A2 squared, or A subset 2, A subset 1 squared, which is the same as this one. And then this is just the notation to go with it, if it's 2D. Oh, so this one means it's 3D. Okay. But yeah, that's the idea in 2D. And then the one with the two vertical lines is for 3D. Right? Yeah, yeah. The textbook says it. So the length of 3D vector A, I'm assuming it's A again. I can use a different one, but whatever. This is A1, A2, A3. And this is the double, I don't know how to call it, but it's the, oh, wait, I'm kidding. It still uses the single one. Okay, not gonna assume anymore. So I could use any, I think. I could use this one, or I could use this one. So it depends. Oh no, I think any works. Yeah, I guess which one will save you ink? That's what you'll use. Yeah, and then this one just has a Z in it, right? So the A1, the A2, and then the A3. It's the same idea as the other one. Okay. Now we're gonna look at it from an algebraic perspective. Okay. Now we ask, how do we add vectors algebraically? We have this figure here. I will screenshot. Not sure if you can see it, but I'll put it. Okay. Wow, looks very complicated, right? I know. I haven't seen it. If A is A1, A2, B is B1, B2. So we're saying A is A1, A2. B is B1, B2. Then their sum is obviously, I'll put like a then. Then A plus B is this thing, obviously, which we have seen in the previous one. right? And we can actually see it from here, which is kind of funny. So we have, where was A? A is this one. See how it has A1 and A2. And then the other one, B, is B1. And then, no, I'm wrong. B1 and B2. So this is, yeah, so this is the B vector. This is the A vector. And so their displacement is A plus B. So you can again look at this in Seattle, Tacoma. And then this is Bothell, right? Yeah. So we go from A to B, then we get A plus B. So that's how we came up with this thing. Now, oh, so that's for adding. Now to subtract, you see that the components of CA and are CA1, CA2. So we to multiply a scalar, no, I'm kidding. To multiply a vector by a scalar, we multiply each component by that scalar. Okay, so that's for adding. So similarly, not sure how this is working. To subtract. Let's look at the figure actually. I'll get the figure. Now to subtract this thing, we see that components of CA are CA1 and CA2, right? So when we add this and this, we get this. So here we see that C is a scalar, is CA1 plus CA2. And so, yeah, that makes sense. Because whatever you multiply this with, you multiply it to here, right? And then we can do something like C times A plus 1, A subset 1, A subset 2. We can divide them. We get A is A1 plus A2. It's just scaling, basically. We get a much smaller rectangle, which is this one. But yeah, that's what multiplying is doing. If we're multiplying a C that's greater than 0, then we're making that triangle bigger. But if we're multiplying something less than 0, no, actually not even less than 0, less than 1. Yeah, then we're making it smaller, something like 1/2, 1/3, 5/6. We're making it smaller than the original. Okay, so it says here, and then this is a bit of jargon, tongue twister. To multiply by, no, to multiply a vector by a scalar. So like C times V, right? We multiply each component by that scalar. Yeah, which we did earlier. Yeah. A is A1 plus A2. We have a scalar of C. So if we multiply C to the left side, then we also multiply everything by C to the right side. That's funny. It's tongue twister, but anyway. Okay, and then here we have I'm just looking at it, I'm overwhelmed, but I'm gonna write it out. So we're saying if A is A1, A2, B is B1, B2, then A plus B is when we add them both. So A1 plus B1, A2 plus B2, and when we're subtracting them, then we also do that accordingly. And if we're multiplying them, we also multiply it accordingly. So this is for 2D. Similarly for 3D, three-dimensional vectors. Oh, it's the same idea. So my A1, A2, A3 plus B1, B2, B3 is just basically adding all of them in one go. So A1 plus B1, A2 plus B2. Let's move it a bit here. Oh shoot, did not mean to do that. Okay, move it a bit here. A3 plus B3. And then when we're subtracting it, then we're also subtracting everything. Oh, it's funny. I put a plus here. B1, B2, B3. So we have A1 minus B1, A2 minus B2, A3 minus B3. Right? Okay. And then finally for multiplying, we're multiplying a scalar by a vector. Then this is just multiplying every single coordinate by that same scalar. Okay, yeah. It looks overwhelming, but it's just basic addition, subtraction, and all that stuff. Yeah. Okay, and then now we apply that. So we're in example 4, and we say, if A is this vector, and B is this vector, we want to find the absolute value of A. And the vectors A plus B I think this is funny because this is just basically this. Or I'm not sure. I think it's just that though. But we'll see, we'll see, we'll see. And vectors a plus b. Yeah, see? I'm new to this. 3b and 2a plus 5b. Oh, so it is different. Oh, lol. Because I forgot. This is our, what was it called? Position vector, right? Hmm. So this is our position vector. So the first thing we can do, since they gave us a lot, is we first have to find the vector A. And this is basically the distance between this point all the way to this point. And we have that 3D distance formula in our toolkit. So this, what do you call that? Is it a vector? What do you call that? Oh, you call it the length of the vector. It's not the vector, it's the length. So to find the length or the distance, then we just do that 4 minus 0, 0 minus 0, which is just 0. Okay, I'll shorten it. So we have 4 squared plus 0 squared plus 3 squared, 16 plus 9. Calculator. Square root 25, which is just 5. Right? So that's that. Okay, now we find a plus b. So what do we know? If we have this vector a and we have this b, and when we add them, we get a plus b, right? So if we're doing that, it's actually quite simple. This a is 403. This b, we're basically just adding the vectors themselves. That's what's happening. Not geometrically, but algebraically. So we're adding them. And how do we do that? Well, we basically add this one and this one, this one and this one, and then this one and this one. Okay, so let's do that. So we have 4 plus negative 2. So 4 minus 2, 0 plus 1, 3 plus 5. So it's just 218. That's the new point we have. We call this a point, right? What do we call this? Because I know the one with the parenthesis is a... Oh, oh, not there. We call this a representation. A vector of something, vector AB with representation. So it's like, how do you represent this thing? Oh, we call them components. Okay. So it's the 3 components, or it's the components of the vector A plus B. So that's that. Then you have a minus b. So same idea, we just subtract them. So a minus b is this thing, we subtract it. So we have 4 minus negative 2. So if it's a double negative, it's positive. So that's 6. Negative 1. And negative 2. Because 3 minus 5 is negative 2. And then I think that should be it. You have more? Oh, you have 3b and 2a plus 5b. So remember that scaling thing, right? So 3b is 3 times the components of b. So we just multiply each. So we have negative 6, 3, 15. Because we basically just multiplied each of those. And then we have 2a plus 5b. Which I think is the complicated one. So we have 2 of the components of the vector A plus 5 of the components of vector B. And so this is what? 8, 8, 0, 6, negative 10, 5, 25. I should put the equal sign here just to make it cleaner. Then we have 8 minus 10, negative 2, 5, 31. I think it should be it. Yeah. Okay, how many more? I'm still checking. Because I feel like this will take a while. Yeah, this will take a while. Okay, I'm gonna leave it at that. At least we went over the basics. And yeah, I'll see you guys in the next video.